Hey, I'm back. And look, not much has changed since the last video, and that's because it's literally back to back. All I changed was just the text over here, really, um, on the side. So let's go ahead and put this back up here. Let's go ahead and erase that. And let's go ahead and start talking linear combinations of random variables. So, oops. Let's say x and y are random variables. Fair enough. Uh, I want to know uh, well, first of all, let's see if we believe this. Then so is x plus y. Sure, that makes sense, right? Like if I have two dice, and so the outcome of dice number one is x, the outcome of dice number two is y. I roll them, I add them together. That's a random variable, right? Its values range from 2 to 12. There's going to be some probability associated to every number between 2 and 12. So it follows all the parameters we'd expect from a random variable, right? Let's see. And we were just talking about uh, in the previous video about playing a game with cards. So like if you're gambling, the outcome of every game is a random variable. And if you keep playing over and over, then you're summing over the course of the night all of the outcomes of all the random variables. And so your overall performance over the course of a night, that's also a random variable, right? It's just a whole bunch of these things summed together. Like you buy a lottery ticket, you buy two lottery tickets, you buy 20 lottery tickets. Those are all random variables. And x and y don't have to be the same, right? You could buy a two different lottery tickets that are for two different types of lotteries. You could play uh, a slot machine and then go play blackjack and go play poker, and those will all be have different, you know, different expected values, different variances, different possible outcomes. But at the end of the day, the sum net gains from all of those is your net winnings or losses for that night or that day. And yeah, that's perfectly legit random variable, right? Bunch of possible outcomes, probability associated with both. So, as usual, then, if I know, let's say, if I understand x, meaning I know its expectation variance, and understand y, I know its expectation variance, then it should be believable that I should be able to find expectation variance for x plus y, right? And so let's first let's state the first fact. So I'm gonna go ahead and move to my cyan color, and the first general fact is e of x plus y is e of x plus e of y. Do we believe that? I believe it. I sure hope you believe it too. It's we can go ahead and work out the details of the algebra because we know we have a formal definition of e of x and e of y and e of x plus y, but it's really not necessary, is it? Um, let's say I roll two dice. What's the average outcome of the first dice? It's 3.5. Average outcome of the second dice is also 3.5. So the average outcome of the two dice together should be 3.5 plus 3.5, right? Should be no great surprise here. Okay, so hopefully we all believe that, and that's good. Then let's ask ourselves, what is the well, let's say, oops, da 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 da. Okay, what about the expectation of c times x, where c is constant. Well, let's say I have a dice, and I take each side of my dice, and I scratch out whatever's written there and write half of what's there. So I scratch out one, I write one half, and I scratch out two, and I write one, then I scratch out three, and I write three over two, and scratch out four, and write two, and so on. If I roll that dice, what's the average outcome? It really ought to be half of whatever the original average outcome was, right? Which was 3.5. And if I doubled all the outcomes, right, well, instead of one, I had two, two for four, three to six, four to eight, etc. I should have doubled the outcome, right? And so sorry. In that scenario, you should just get c times whatever the original average outcome was, right? And hopefully that makes sense as well. So then let's move on to variance. Now, oops. So let's ask ourselves, what is the variance of x plus y? So let's think back again to rolling dice to give us some intuition. And let's say the first dice has some amount of variability, right? So when I roll the first dice, it goes from 1 to 6, and there's a range of outcomes. When I roll the second time, there's some range of outcomes. And when I combine the two dice rolls, there's a bigger range of outcomes, right? And so it makes sense to like add on the second die roll that the total amount of variability in the system increases, right? That it gets more variable, and in fact, it should increase proportional to uh, the the variability of the or in relation to the variability of the individual random variables. And in fact, not only does it do that, it's exactly that. The variance of x plus y is the variance of x plus the variance of y. All right, so hopefully that's helpful there. Now, here's a tricky bit. Well, maybe let's not do the tricky bit just yet. Let's do variance of cx first. So, if I take my die rolls and I like double or triple all the values and roll that dice, it should get more variable, right? And that seems to make sense because I'm blowing up the range of values. But it doesn't blow up exactly proportional to C the way expectation does. And this is because of how expectation is or variance is computed. So recall that the variance of Cx is definitely the expectation of Cx squared minus the expectation of Cx squared. Right? Do we all agree with that? And then so this first term is the expectation of c squared x squared. And then the second term is, well, I can pull a c out of here. So c e of x and all of that squared, right? Now, we recall that we talked about the expectation of a constant times a random variable. We can just pull the expectation out, right? So in the first case, I get c e of x squared, c squared e of x squared minus, and I've applied the square through here, right? I've applied this square to this term here. I get c squared e of x squared. I can factor out a c squared, and that's e of x squared minus e of x squared, and that's c squared times, and what is the second term here? Darn. I'm going to write it over here, I guess. And that's going to be c squared. What is this term here? This is by definition the variance of x, right? You should watch the previous video for a brief explanation of that, but that's the variance of x, right? So bottom line was that this is equal to that, right? C squared variance of x. So when I pull constants out of the variance, I square them. All right. So give us a moment, and before I erase this whole thing, and all right, there it is. Okay, great. So let's go ahead and talk about what the implications of that are. So actually, I'm going to keep the same color. What's the expectation of x minus y? Well, do we believe it's expectation of x plus negative 1 times y? And our first property from our previous slides, do we believe that that means that that should be e of x plus e of negative 1 times y? Oh, what? Oh my god. I just realized something great. Okay, never mind that for now. So here I have e of x plus negative 1 times e of negative 1 times y. And the last thing we said was that I get to, for expectation, pull out constants. So I can pull out the negative 1, and I get the average value of x minus the average value of y. And that seems like common sense, right? Like again, if I roll 2 dice, the average outcome of the first dice is 3.5. The average outcome of the second dice is 3.5. If I take a difference between the die rolls, that really ought to be 0 on average, right? So the biggest you can get is 5, which is 6 minus 1. The smallest you can get is negative 5, which is 1 minus 6. And of course, all the values in between are possible, but really on average, if both of the die rolls have the same average outcome, then when I take their difference, that really ought to be 0. Okay, so what's the variance of x minus y then? Well, we could try to follow along the same thought as we did with the expectation up here. So for variance, let's say that that's definitely also var x minus or plus -1 y, which is var x plus var -1 -1 times y, right? Which is, sorry, var x plus -1 squared, right? Remember that when we pull constants out of the variance, we square them, var y, which is var x plus var y. Oh, hold on, that's very different, right? This is a very different result than what we got here. We take the difference between two dirows, we expect the average value to kind of cancel, right? We take the difference between the variance of two dirows. Why do we add the variances here? Does that make any sense intuitively? Well, what is, if I did take two dirows, take the first dirol, subtract the second dirol, how variable is that exactly? It's definitely not. It's definitely not that, right? There's no way it could be that. And just think about it, right? Roll two dice. They both have variance 2 point, I don't remember exactly, 98 something. Uh, they're identical in terms of behavior. So if I take the difference, their variance is 0. But we just said that the values could range from -5 to 5, and that doesn't sound like no variance to me. That sounds like a lot of variance to me, right? And so what we see here is that, if I have, let's say I roll a dice and it has variance 2.98 or whatever it does. And then I subtracted exactly 3.5 from that. Then that thing that I get from doing that process, that thing has, I'll go away, I'll pay for you at some point. That thing has exactly the same variance as it did originally, right? All we did was take the dirows range 1 through 6, and then we shifted them over by whatever we decided to shift them over by. They're not any more variable, right? They're just sitting somewhere else on the number line. Mm-hmm. But if I take my dirows, or wherever they are, and then I subtract them by a random value, then there's a lot of possible places that sort of range can now land, and now I have a more variable collection of outcomes. In other words, the randomness of the first random variable is compounded by the randomness of the second random variable. And so what that means is, frankly, that that things get more variable, right? And another reason the variable x minus y couldn't possibly be this is, what if y was more variable than x? Okay, then take variable x minus variable y. So that variance be negative. I'm not even sure what that would mean, right? What does it mean to be negatively varied? The least variable a random variable could be is if it's constant, if it only has one outcome, because that's what it means to not have variation, right? So, uh, so let's go ahead and skip ahead, and I'm going to use this awesome feature I just discovered to pop forward because I want to reference those slides again. I'm going to pull this thing down, pull that thing down. Yeah, I'm done with that. Let's take a look at ice cream. That's a good one. So we have, hey, you know what? That Y should be blue like everything else. Give me a second here. Ah. There we go. Okay, so we have our two random variables, x and y. They're both measured in fluid ounces, so we made that easy for ourselves. So the ice cream comes in quart boxes, so that's what x is. And on average, they have 48 fluid ounces, but of course, there's some variation because nothing's perfect. And the ice cream scoop holds uh, 2 ounces, and there's some various stand variance there because it's also not perfect. And so, if you serve an entire box of ice cream plus 8 scoops, you want to know how much ice cream is served here and what the standard deviation of that is. And so, all right, fair enough. Well, how much is left? Let's say left is a random variable, is x plus y plus y plus y plus y plus y plus y. 1, 2, 3, 4, 5, 6 plus y plus y left, or sorry, served. Right. So E of S is the expectation of this random variable, right? Which is E of x plus y plus dot 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 plus y. And we should already kind of know what to do with this, right? That is E of x plus, why are you doing this? We should be able to just compute that by, the expectation of x plus expectation of y plus expectation of y, so on and so forth, with 8 y's and 1 x, right? And the variance really ought to be the same thing, right? It should be the variance of x plus variance of y plus dot 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 variance of y, right? And then the standard deviation for S is just the square root of the variance of S. And good thing for us, the expectation and the variance are right there. So, ta-da, that part is fairly straightforward. Hopefully that helps. The second part of this problem is like, all right, you take a box of ice cream and you take out 1 scoop and you wonder what's left. So, all right, that's easy enough. Left is x minus y. Right? And if x is s minus y, then we already know what E of L ought to be, right? Oh, E of L and variance of L. The expectation of L, we literally just did this, right? It's the expectation of X minus the expectation. Okay, this is starting to stress me out a little bit. My app here is not doing what I want it to do. Expectation of Y, and then the variance is the variance of X plus the variance of Y, right? And that, again, we talked about this in the previous slides. Let me pop back here, right? We said, all right, the variance of X minus Y is the variance of X plus the variance of Y. And the reason is, of course, there's an algebraic reason that's given on that slide, but the real sort of intuitive reason is there's some randomness with the box of ice cream already, and on top of that, there's some more randomness with the ice cream scoop, so we put the randomnesses together, and we'll have the variance of what's left in the box. And then, of course, sigma is square root of the variance. All right, so hopefully that helps. I recommend, again, maybe going to Desmos to doing these computations so they're not terrible to do by hand. So if I wanted to find out what the expectation, what the expected value, say, of S was, then, I could say something like, it's 48 plus 2, or sorry, 8 times 2, right? I could give that a name just so it's easier to keep track of. Maybe E of S is equal to that. Then the variance of S, maybe I'll call it the variance of S is equal to 1.21 times plus 8 times, I'm not going to remember that. Copy and paste is the best. All right, and of course the standard deviation of S is just the square root of variance of S. And, so on, right? You can do the same thing for L. All right, so hopefully that was helpful, and those are our videos discussing the linear combination and expected value and variance of random variables.